Welcome to this presentation where we want to look at numerical methods for partial differential equations. This is university mathematics, all right? Okay, so what is it that we want to look at in this video? Okay, we want to look at one specific approach, which is the finite difference method or approach. Okay, we have got the shooting method, so on and so forth. But in this case, we want to look at the finite difference method or scheme. Okay, let's look at the question. We are saying find the finite difference solution for the heat transfer boundary value problem for a load of length 1.1 centimeter and given by this differential equation. Okay. Dt squared divided by dt, dx squared minus beta squared t is equal to negative beta squared ta, where beta squared is 16 square centimeters, that is the heat diffusivity, and ta is 20 degrees, that is ambient temperature, subject to the boundary conditions. T of 0 is 25, and T of 1 is this must be 75, because it will then mean that it must be the same. Okay, this is the 75. Okay, now use the step size of 0.25. Okay, so how do we solve this with this step size? Okay, let's see our solution. Okay, the first thing is maybe we can rewrite our equation. Can write our equation, our differential equation, partial differential equation. Our differential equation just, that is dt dt squared divided by dx squared minus beta squared t is equal to negative beta squared ta. So we can write this, okay? So this will imply that we have dt squared divided by dx squared, this is the same as beta squared t minus beta squared ta. Okay, we can still rewrite this. We can say this is the same as this is, since this is a second derivative, we can just say t double prime is equal to, but our beta has been given to be 16 beta squared, so we have 16t minus 16, then our TA has been given to be 20. Okay, yeah, I'm comfortable with that form. So T double prime is equal to 16t minus 320 when you work it out. So this is the differential equation that we are going to use. All right. Okay, now we know that we have h being equal to 0.25. Now, when you look at the boundary conditions, we go to the boundary conditions, we look at the boundary conditions, we have t of 0 and t of 1. So it means our lower limit, if I were to say it that way, is 0. Our upper limit is 1. So it simply means, now we know that h is given by b minus a over n. Okay, implying that our h is a 0.25, our b is the upper boundary, which is 1 minus 0 divided by n, implying that n, when you do your calculations, n will be 4. So we'll have 4 equal subintervals. All right? Then from here, we can discretize our interval. We say discretization. Okay. Discretization. So this is x naught is 0. X1 is, so when you add 0 to 0.25, you have got 0.25. Then we have x2 is equal to 0.5 when you add. Then x3, 0.75 when you add. Again, when we add the 0.25, we have x4, that is 1. Here you can say I is equal to 0, 1, 2, 3, 4. Now, for the finite difference method, we get the inner nodes. So we'll pick I is equal to 1, 2, 3. This is what we are going to pick. Now, since our differential equation has got the second derivative, we can apply the central difference. So we are going to have central difference, and to apply the central difference, so we can say by central difference approach, okay, we'll have ti1 minus 2ti plus ti minus 1, everything here divided by h squared. So that this part has been replaced by what is down here. Okay, maybe the best way is, for sake of reference, the best way is, let me rewrite this so that we are able to refer to this. Remember, after rewriting our differential equation, we had t double prime is equal to, I think, 16t minus, I think, 320. So we are saying this part here, it is this one, which is here. Okay, that's what we have. Okay. So now we can proceed. So now for us to come up with an equation, nice, it's better. All the variables are on the same side. So I can take t, the other side, 16t. So it becomes minus 16ti. And this will be equal to negative 320. So you multiply throughout. By h squared. So what are we going to have? So we'll have ti plus 1 minus 2ti plus ti minus 1. So this will be minus h squared 16 ti is equal to negative h squared 320. Okay, so I can start with the ti minus 1. So I have ti minus 1 because I'll move from 1 to up to 4 in terms of equations. So you have maybe t1, t2, so on and so forth. So it's better to start with t1, ti minus 1. Then you can put this and this one, put them together. So you're going to have minus 2ti minus h squared 16ti plus ti minus 1 is equal to negative h squared 320. So ti minus 1 plus, we can factor out what is common, that is ti. So we have negative 2 minus h squared 16 ti plus, this is supposed to be plus, ti plus 1 is equal to negative h squared 320. Okay? So now we can substitute. We know that h is a 0.25 and yeah, basically that's what we have. Okay? So we have ti minus 1 plus negative 2 minus h is a 0.25 squared 16 ti plus ti plus 1 is equal to negative 0.25 squared so negative 0.25 squared 320. So here we're just doing the substitution. Okay, I hope it is clear up to this far. So now we have ti minus 1. So what do we get here when we work out here? What do we get here? So when you simplify, you can use your calculator. What are you going to get? So the whole lot of this one will give you negative 3. The one that I've underlined here. Now there's ti here. Plus ti plus 1 is equal to, again, what is here, when you work it out, you get negative 20. So this one is our this is our scheme, our finite difference scheme. But now we want to find the finite difference solution. Okay, so we must find T1, T2, T3 up to, I think, T4. So we have I. Remember we said we are dealing with the inner nodes. So we'll have I is equal to 0, 1, inner nodes only. From our discretization, we have 1, 2, and 3. So we'll have only T1, T2, and T3. Because we are dealing with the inner nodes only. So this is what we are talking about. From here, 1, 2, 3, we leave out that because it will overshoot. Okay. So now, we can now transform this finite difference scheme. This is a finite difference scheme, the one that we found. So we can transform this into linear equations. So when I is equal to 1. What are we going to have? So if you put 1 here, so there'll be 1 minus 1. So we'll have T0 minus 3T1 plus T2, 1 plus 1 is equal to negative 20. But T0 is equal to 25 from the boundary conditions. So we'll have, where there's T0, we put 25 minus 3T1 plus T2 is equal to negative 20. So upon grouping the terms, we are going to have negative 3T1 plus T2 is equal to negative 45. This is our first equation. Equation 1. Hope that is okay. That is our first equation. Then, when I is equal to 2. So from our scheme, so if you put 2 here, we have T1, T2, T3. So we are going to have T1 minus 3 T2 plus T3 is equal to negative 20. This one becomes our equation 2. Then when I is equal to 3, so it will be 3 minus 1, so we'll have T2 minus 3 T3 plus T4 is equal to negative 20. Okay? But now, T4 is our boundary. If we go back to our discretization, if we come back to our discretization here, T4 is the boundary here. Okay? The boundary. So you get now the value from the boundary condition of the upper limit. So if you look at our boundary condition for the upper limit, T0 was for the lower limit, we got 25. But T4, it is for the upper limit. And what is the value for the upper limit? 75. So that's what we mean by T4, or that's what we'll get for T4. So we are going to have T2 minus 3 T3 plus 75. This will give us negative 20. Therefore, T2 minus 3 T3 is equal to negative 95. And this is our equation 3. So now we can rewrite these equations in terms of matrix or matrix equations. Okay? Then we'll be able to solve them. So we'll have from the first equation, from our first equation, we'll have, when you pick the coefficients, you have negative 3, 1, and T3 is 0. From the second equation, we have got 1, negative 3, 1. From the third equation, you have got 0, T1 is 0, so it's 0, 1, and negative 3. Okay, so we are going to have negative 3, 1, 0. Then you have 1, negative 3, 1. Then 0, 1, negative 3. This is what we are going to have. So we multiply this by T1, T2, and T3. But what was on the right-hand side of equation 1? We got negative 45. Here we got negative 20. And the last one we got 95. Okay? You can use whichever method that you are comfortable with. Okay? But I can use the Gaussian elimination. Back substitution. So when I use this, what do we mean? What we mean is that we need to produce zeros. I need to have a 0 here. Here it's already there. I need to have a 0 and a 0 there. All right? That's what we want. So what does it mean? It simply means I can say row 2 is equal to row 2 plus 1 over 3 row 1. Okay? And what does this give us? So it means row 1 will not be affected, negative 3, 1, 0 here. Okay? Then here we have negative 45. Now for row 2, so if you take 1 here, you put 1 here, you put 1 here, and here you put 3. Here you put negative 3. Of course, 3 by negative 3 to be negative 1. When you add, this part will be, will be 0. Okay? And that's what we want. Then applying the same, what are you going to get? You get negative 2.6. That's what you are going to get there. Then for this one, so if you put 1 here again, then here you put what? 0. You get your 1. Here you get negative 35. What do we mean? You say negative 20 plus 1 over 3, row 1 is negative 45. So this will give you negative 35. And the last one is not affected. So you have a 0 already here. So you have your 1, negative 3, and negative 95. Okay. Then we can go to, we change this. We change this, we convert this to 0. So we'll say row 3 is equal to row 3 itself plus 1 divided by 2.1, 2, 3, 4, 5, 6, 7, 8, 9, and 7. Then you multiply this by row 2. Okay? So it means row 1, row 2 now will be repeated. What are you going to have? You're going to have negative 3. You have 1, 0. Then here we have negative 45. So row 2 is 0, negative 2 point. Okay. Then there is 1 and negative 35. Here there is 0. So this part now will change, because if you put 1 here, then you put negative 2.666 all the way up to 7. the answer will be 0. So here, let me maintain this because that's our interest. We get 0 here, 0 here, and eventually here, this one will be 0. Proceeding in that manner, this one will be negative 108.124 9999. Okay, it continues here. I think there are 24698. Okay, take note. I think this, from my calculation, this I got 2.625. I think so. Then the other one is the negative 10, 8.124 now. Yeah. 9999 98. There are 7 of them there. You can counter check with your calculator. Okay. From there now we can find T3. That simply means this implies that negative 2.625 T3 is equal to negative 108.124 99999998. So dividing by negative 2.625, negative 2.625, what do you get? So therefore your T3 will become 41.190476 This is your solution for T3. But we can maybe round it off to 4 decimal places, 41.1905. This is our solution. Okay. So you can now do the back substitution for the other two and confirm that your T2 will be 28.5714 and T1 will be 24.5238. This is what you're going to get. Okay, please, thank you for watching. Share with your friends. Subscribe to our channels. Kanban, phiri-JM. Chaomba Mbondo. See you next time. Bye-bye. God bless.